Okay, for last week's update, I went over the basics of the problem and my approach for calculating the maximum stress by assuming it to be a cantilevered beam and applying basic strengths of materials to solve. This week I created a CAD model of 5 different L brackets and verified that they would properly mesh in the COMSOL software. I locked down a loading force of 100 pounds spread evenly between 2 bolts. Also, I verified the COMSOL model for the L bracket against the calculated stress and found the most accurate boundary conditions and loading conditions. Finally, I found what size mesh the solution converges. Here's the basic bracket model with an extra fine mesh. Here's the formed bracket. Here's the flanged bracket. Here's the flanged bracket with fillets around the flanges. And finally, here's the isogrid bracket. Originally, I had issues meshing this, but putting a small radius in the area circled helped meshing go smoother in COMSOL. With the 100-pound total load, the individual force each bolt sees is 500 pounds. Here's the updated calculated stress that I used to verify the model. Here are the boundary conditions that I found most accurately represents a bracket bolted to a rigid wall with a vertical force going through bolts on the other end. The force is transmitted through where a washer would contact the bracket. The displacement constraint resembles where and how a bolt would contact the bracket. And here are my results. For the basic L bracket, the maximum stress in COMSOL was about 10 to 40% larger than the calculated stress. I believe this to be due to the cantilevered bar assumption that was made for the hand calculations, and also the sharp edge at the corner of the L bracket could cause a stress concentration that would explain why COMSOL found a larger maximum stress. Here are the stress and displacement results from the COMSOL model. The bracket deforms as expected. I highlighted the area against the wall to show that it is free to move, which is how a real bracket would behave.